Year 13 Differential Equations, Lesson 4. So we're going to have a look at two examples of simpler word problems involving differential equations, and we're then going to look at a series of exam-style questions which make use of all of the different techniques that you have come across so far. So let's read example 1. We know that the number of bacteria is increasing, that's important, at a rate that is directly proportional to n. The time t is measured in hours. So part A, find the differential equation relating n and t. So we can make use of this information regarding proportionality. And we can say that dn by dt, which is the rate of change of the population number of bacteria, is directly proportional to the number of bacteria present at time t, and we can then turn this from a proportionality relationship into a differential equation. Dn by dt equals kn, and we're looking at some constant k here. Now, part B, show that the general solution can be expressed in this form here, where a and k are constants. So let's separate variables and integrate. So I can say that 1 over n, integral of with respect to n, is equal to k, the integral of dt, and if you want to, you can put a 1 there to help you. So a very simple integration here, ln of n. Now n is number of bacteria, it's got to be greater than 0, so I'm going to just leave it as ln n rather than ln mod n. And this equals kt plus c. Now we need to express it in the form n equals, so n equals e to the kt plus c, which is e to the kt multiplied by e to the c, and of course we can then write this as n equals a e to the kt, whereby we let e to the c equal a, so we get the relationship needed. Part C, we are given some information. When t equals 0, n equals 40, and when t equals 5, n equals 60, because of course there are two unknowns we've got to find, the value of a and the value of k. So let's sub in this first piece of information over here, and this tells us that 40 is equal to a, because e to the power of 0 is just 1. So for this second piece of information, we can now say that 60 is equal to a, which is 40, e to the power of 5k, because t is 5. Now let's divide both sides by 40, which gives us 1.5 equals e to the 5k, ln of 1.5 equals 5k, and k is equal to 1/5 of ln 1.5, which I will leave in exact form for the moment. So, the next part of the question, find n when t equals 12 hours. So I can say that n is equal to a, which is 40, e to the power of k, I'll just write it as k for the moment, multiplied by 12, and of course we know the value of k there. Let's sub this into our calculator. So this gives an answer of 1903.65 ... which I might round to, let's say, 1904 to the nearest whole number. Now the last part of the question asks us to sketch a graph of n versus t. So you can also have a look at doing this on your calculator. So we know when t equals 0, n is equal to 40. We're looking at a relationship of exponential growth here. So the graph will simply look something a little like this. Let's look at the second example. At time t equals 0, a piece of radioactive material has a mass of 240 grams. Its mass after t days is m grams and is decreasing at a rate proportional to m. So, some useful information here. The mass is decreasing at a rate proportional to the amount that is present. So, form and solve a suitable differential equation. So we know the rate of change of the mass, dm by dt, is directly proportional to m, but it's a negative rate like that. So we can then write dm by dt equals negative km. And then if we separate the variables, 1 over m, integral of with respect to m, is equal to the integral of negative k dt. The k could come before the integral sign as well, as it's just a constant. So ln of m, again it's a mass, so it can't be negative, so I won't include a modulus, equals negative kt plus c. So I can then say that m is equal to e to the negative kt plus c. Now, let's split up the exponential on the right-hand side. So we have e to the negative kt multiplied by e to the c. So m equals ae to the negative kt. Now, we are told at the start that when the time t equals 0, we have a mass of 24 grams. So let's substitute in that information. So 24 is equal to a, because e to the 0 is just 1. So this gives us the relationship m equals 24e to the negative kt, which we were required to find. So part B. After 20 days, the mass of the material is found to be 22.6 grams. Find the value of k. So we can say 22.6 is equal to 24e to the power of negative k multiplied by 20. Let's divide both sides by 24. So 22.6 over 24 equals e to the negative 20k. And then, of course, taking natural logs of both sides gives us this result over here. And then we simply need to divide both sides by negative 20 to find our value of k. So this gives k equals 0.003005 ... So 0.003 to 3 decimal places. Part 2. Find the rate at which the mass is decreasing after 20 days. Now, rate means it wants us to calculate dm by dt, not m, because it's the rate of change. So we have the relationship over here, dm by dt equals negative km, and we now know the value of k over here. So dm by dt is equal to negative 0.003 ... multiplied by the value of m. Now, how do we find the value of m? We use this result over here. So we so far have negative k. We need to multiply by m, which can be calculated with 24e to the power of negative k multiplied by the time 20, and we can input this into our calculator. So this gives us a rate of negative 0.0765 ... which I will round to negative 0.077 grams per day, to 2 significant figures. So find out how long it takes for the mass of material to be halved. So if the mass of the material halves, then we're looking for a mass of 12 grams. So we want 12 to equal 24e to the negative kt. Let's divide both sides by 24, so 0.5 equals e to the negative kt. ln of 0.5 equals negative kt, and then divide both sides by negative k to get the value of t. So this gives t equals 230.664 ... days. So let's say 231 days to 3 significant figures. And that is, of course, the half-life, the time taken for the radioactive mass to decrease to half its original value. So next part of the question, sketch a graph of m versus t. So here we have m versus t. Now, at time t equals 0, we know the mass is 24. So we have a y-intercept on our graph of 24 grams, the starting mass, and we know it is reducing. Now, if we look at this result over here, the equation for m versus t, if we allow t to approach infinity, m will approach 0. So the x-axis, or the t-axis, is an asymptote for the graph, and we have exponential decay like so. So we're now going to have a look at a series of different exam questions involving differential equations, which will make use of a range of the different techniques that we have covered in the last few lessons. So, example 1. We are told that a drug is administered by an intravenous drip and the concentration, X, of the drug in the blood is measured as a fraction of its maximum level. The drug concentration after T hours is modelled by this differential equation here, where K is a positive constant and initially X equals 0. So part 1, we've very helpfully been asked to decompose this fraction into its constituent partial fractions. No doubt we will need this later on during the integration. So I'll write it out as its separate fractions, and then we will combine them so we have this result here. I'm going to choose values of x to substitute in. I'll choose x equals 1, which gives me 1 equals 3b. So b is equal to 1/3. And then I'm going to choose x equals -1/2, which will give me 1 equals 3/2a, so a is equal to 2/3. So now we can write our partial fractions as 2/3 1 plus 2x plus 1/3 1 minus x. Now part 2, we have to solve this differential equation from the first part of the question. So separating the variables, we have 1/1 plus x minus 2x squared dx equals the integral of k dt, and the k is a constant, so it could come out of the integral sign. Now we know that if we factorise this quadratic, it will factorise as follows, and the right hand side simply integrates directly to kt, and we'll put in a constant there, c. Now the left hand side, we need to integrate this, but of course that's the same as integrating this pair of partial fractions from earlier on. So the integral is 2/3 1/1 plus 2x dx plus 1/3 the integral of 1/1 minus x dx. So that integral would be 1/3 ln mod 1 plus 2x minus 1/3 ln mod 1 minus x. And we don't need to include a constant because it's included on the right hand side. So this gives me 1/3 ln mod 1 plus 2x over 1 minus x equals kt plus c. Hopefully you can see that I've factorised out the third and I've combined the two logs. Now, we need to multiply both sides by 3, but actually before we'll do that, we'll work out the value of this constant, because we were told that initially x equals 0. So when t equals 0, x is equal to 0 as well. So that tells me that 1/3 ln of 1 equals k multiplied by 0 plus c. Ln of 1 also equals 0, so this constant c equals 0. This makes things very much easier. When we multiply by 3, we simply get ln 1 plus 2x over 1 minus x modulus of equals 3kt, and then all that's left is to raise e to the power of both sides, which gives us e to the 3kt equals 1 plus 2x over 1 minus x as required. So part 3, we are told that after 1 hour, the drug concentration reaches 75% of its maximum value, so x is equal to 0.75. Because remember, the concentration of the drug is measured as a fraction of its maximum level. So find the value of k and the time taken for the drug concentration to reach 90% of its maximum value. So what can we do? We can substitute this information into our general solution, which was over here. So that gives us 1 plus 1.5 over 0.25 equals e to the 3k, and taking logs of both sides, that's ln of 2.5 over 0.25 equals 3k, and then divide that by 3 to find our value of k. So we could write k equals a third ln of 10. We could also work out the value as a decimal as well. Now the time taken for the drug concentration to reach 90% of its maximum value, so that means that x is equal to 0.9. So this tells us that we have 1 plus 1.8 over 0.1 equals e to the power of 3 multiplied by k multiplied by t. So we need to take natural logs of both sides. So this gives us ln of 28 equals 3kt. Divide both sides by the value of 3k, and this gives us t. T equals 1.4471 ... which is equal to 1.45 hours to 3 significant figures. Now, part 4 takes us on to some algebra. Rearrange the equation to show that we get this result here. So we need to change the subject and make sure it's in the form x equals. So first job, we'll multiply across by 1 minus x. So 1 plus 2x equals e to the 3kt, 1 minus x. Then 1 plus 2x equals e to the 3kt minus x e to the 3kt, expanding the brackets. Then I'm going to collect the terms that feature x on the left-hand side. Anything else moves across to the right-hand side like so. Factorise x on the left, so 2 plus e to the 3kt equals e to the 3kt minus 1. And then divide through by this bracket here, 2 plus e to the 3kt, which gives us x equals e to the 3kt minus 1 over 2 plus e to the 3kt, which is not quite this answer here. So to achieve the answer there, we actually need to multiply. Well, there are different ways of doing this, but this is one way of doing it. Multiply both the numerator and denominator by e to the negative 3kt. As long as we do it to both numerator and denominator, this is a valid mathematical step, and we still have an equivalent result. So e to the 3kt multiplied by e to the negative 3kt will give us a power 0, which gives us 1. So we have 1 take away e to the negative 3kt, and then in the denominator, something similar, 2e to the negative 3kt plus 1. So we have the result we needed. Now, verify that in the long term, the drug concentration approaches its maximum value. So in the long term, this is where t approaches infinity. Now, as t approaches infinity, e to the negative 3kt will approach 0. You can test that on your calculator if you want to, or think about the shape of an exponential graph. Now, that means that x here in the equation for x, this part here will approximately be 0. This part here will approximately be 0 as well. So x will approximately be 1 over 1, i.e. x will approach 1. Now remember, x was a fraction of the maximum level. The maximum level fraction being 1 tells that x approaches its maximum value in the long term. Example 2. So we have a diagram that shows an upright cylindrical barrel containing water. The water is leaking out of a hole in the side of the barrel. The height of the water surface above the hole t seconds after opening the hole is h meters, where the differential equation giving us the rate of change of the height with respect to time is here. And a is a positive constant. Now initially, the water surface is 1 metre above the hole. So that tells us when t equals 0, h equals 1. Now verify that the solution to the differential equation is this. Now, we have two options here. We can separate variables and integrate, or, because it does say verify, we could differentiate this result and show that it satisfies this differential equation. So it's interesting to have a look at the different methods here. So I could just differentiate. So dh by dt, well, this is a chain rule, it's a composite function. I'm going to multiply by the power of 2, reduce the power by 1, so it becomes a power of 1, and then I'm going to multiply by the derivative of the innermost function here, which gives me negative a half a. So this then gives me negative a bracket 1 minus a half a t, and you can see that we have the negative a part here, and we have the square root of h, because of course if h is this statement here, the square root of h is 1 minus a half a t. So this is negative a root h. Now the alternative method here is to separate the variables. So we have the integral of 1 over root h dh equals negative a integral dt. So I've taken my differential equation and separated the variables. Let's rewrite the left-hand side as h to the negative half. Integrate the right-hand side, put in a constant there. Then the left-hand side becomes 2h to the power of a half equals negative at plus c. Now, we're given this piece of initial information, t equals 0 and h equals 1, which gives us 2 equals c. So that tells us that we can rewrite this result here as 2h to the half equals negative at plus 2. Now let's divide both sides by 2, which gives us h to the half equals negative a half at plus 1. And then h will of course equal the square of this, which gives us this result here. So you can see there's two possible methods here, and perfectly valid to use the first method. Look at the wording of the question, verify, which is a way of saying show that this works. So the next part of this question, the water stops leaking when h equals 0. This occurs after 20 seconds. Find the value of a and the time when the height of the water surface above the hole is 0.5 metres. So, as ever in these questions, be careful because there is more than one thing to do in the question, and you're often given information above the question as well. So let's look at part 2. Now, in the last part of the question, we learnt that h equals 1 minus a half a t squared. So h equals 0 when t equals 20. So let's substitute in that information. 0 equals 1 minus a half a multiplied by 20 all squared, which tells us that 1 minus a half a multiplied by 20 equals 0. So 10a equals 1. A is equal to 1/10 or 0.1. Now we need to find the time when the height of the water surface is 0.5. So we'll make h equal to 0.5 and find t. So 0.5 equals 1 minus a half, and we now know that a is 1/10 t all squared. So square root both sides, and we're left with 1 minus 1/20 of t on the right hand side. Let's just solve this simple equation to find t. So this gives me t equals 5.8578 ... So we will say 5.86 seconds to 3 SF. Now the next part of the question looks at a similar situation but with a different barrel. So for this barrel, the differential equation telling us about the rate of change of the height of water is given like so. B is a positive constant, and we're given some conditions over here. Now this time, in the wording of the question, it says solve this differential equation. It doesn't say verify a particular solution, so we now need to separate the variables of this. So separating the variables, I've got 1 plus h all squared over root h equals, with respect to h, integral of, equals negative b, the integral dt. Now, we have seen an integral like this in a previous lesson and how to do an integral like this in a previous lesson. So let's look at the left-hand side. We're going to expand the numerator, so 1 plus 2h plus h squared, and we're going to rewrite the denominator as h to the power of a half. We'll divide every term in the numerator by h to the half, so h to the negative a half, plus 2h to the power of a half, plus h to the 3 over 2, all being integrated with respect to h, and we can then carry out the integration. So this gives us 2h to the half, plus 4/3 h to the power of 3 over 2, plus 2/5 h to the power of 5 over 2, plus a constant as well. So let's go back to the differential equation. And here we have the left-hand side. And on the right-hand side, we will simply get negative bt. And I included the constant on the left-hand side. So remember the conditions: when t equals 0, h is equal to 1. So this then gives us 2 plus 4/3 plus 2/5 plus c equals 0. So from here we can work out the value of c. It is negative 56 over 15. So this then gives us, and I will move up here, the result that we have 2h to the half plus 4/3 h to the 3 over 2 plus 2/5 h to the 5 over 2 equals 56 over 15 minus bt. So I'll move the constant over to the right-hand side. So the last step of this is to multiply both sides by 15. As you can see, we're aiming to get to this result over here. So multiplying both sides by 15 gives me 30h to the half plus 20h to the 3 over 2 plus 6h to the 5 over 2 equals 56 minus 15 bt. And then you can see here they've factorised out h to the half. So let's do that. So h to the half outside. So we have 30 plus 20h plus 6h squared equals 56 minus 15 bt. Now, on to part 4. We'll just make a little bit of space for ourselves here. Given that h equals 0 when t equals 20, find b. So substituting h equals 0 in means the whole of the left-hand side will become 0 because of this h to the half here. So we have 0 equals 56 minus 15b multiplied by 20. Rearrange that to get the value of b, which gives us b equals 56 over 300, or as a decimal, 0.186 recurring. And find also the time when the height of the water surface is 0.5. So for the last part of this question, we want to make h equal to 0.5 and find the value of t. So 0.5 to the half multiplied by 30 plus 20 times 0.5, which is 10. Remember, I'm substituting into this result up over here. Plus 6 multiplied by 0.5 squared, and that is equal to 56, subtract 15, multiplied by b, multiplied by t. So this really just involves some simple rearrangement to find the value of t, which then gives us t equals 9.52 seconds to 3 significant figures. Right, example 3. Data suggest that the number of cases of infection from a particular disease tends to oscillate between 2 values over a period of approximately 6 months. Suppose that the number of cases, p thousands, after time t months is modelled by this equation here. And when t equals 0, p equals 1. By considering the greatest and least values of sine t, write down the greatest and least values of p predicted by this model. So the greatest value of sine t is of course 1, and its minimum value is of course negative 1. Now, if we want to work out p maximum, then we want to make the denominator as small as possible. So that means we need to work out 2 divided by 2 take away 1, which gives us P max is equal to 2. Now, P minimum, we want to make the denominator as large as possible, which it will be if sine t equals -1, because we then have 2 over 2 minus -1, which gives us 2/3. Part 2, verify that P satisfies this differential equation. So as you've seen previously, I could separate variables and integrate, but it's often simpler just to differentiate. So my equation for P is up over here. We need to differentiate it. So I'm just going to rewrite it. P equals 2 brackets 2 minus sine t to the power of -1. I could have differentiated it in its original form, perhaps by making use of the quotient rule, if I wanted to. I'm actually going to make use of the chain rule, which I think is a little bit quicker. dp by dt, multiply by the power, so -1. Reduce that power by 1, which gives us -2, and then multiply by the derivative of the inner function here. I'm using the quick version of the chain rule rather than writing out all of the steps here. Now, negative sine t will differentiate to give me negative cos t. So this all then simplifies to give me 2 over 2 minus sine t all squared, and then we have a cos t at the end. So this, of course, would be equivalent to a half of 4 over 2 minus sine t all squared. And we can see, hopefully, quite clearly that this a half and this 4 would cancel to give me the 2 that I have there, multiplied by cos t, which is a half p squared cos t. And this result here is, of course, the square of p over there. So part B, an alternative model, is proposed with the differential equation here, slightly more complex, and we're given the same initial conditions here. So our first task is to express 1 over p bracket 2p minus 1 in partial fractions. So let's do this. 1 over p 2p minus 1 can be written as a over p plus b over 2p minus 1. So 1 is equivalent to a bracket 2p minus 1 plus bp. Let's choose our values carefully. P equals 0 gives me 1 equals negative a, or a equals -1. And then p equals a half gives me 1 equals a half of b, so b is equal to 2. So my partial fraction decomposition of 1 over p 2p minus 1 is simply 2 over 2p minus 1 minus 1 over p, writing the terms the other way around. Now, part 2, solve the differential equation up here to show that we get this result here. So, separating the variables, we clearly have 1 over 2p squared minus p dp equals the integral of cos t dt, and I'm going to keep the half on the right hand side. So I've separated my variables. Now, on the left hand side, this part here is obviously an expanded version of p bracket 2p minus 1, and we know that it simplifies to this pair of fractions here. This is why we were asked to do the first part. So I can simply rewrite the left-hand side as 2 over 2p minus 1 dp minus the integral of 1 over p dp. I could write it as a single integral. I've chosen to write it as a pair of integrals. On the right-hand side, cos integrates to sine, and we'll put in a constant there. So, integrating each of the parts on the left-hand side in turn. So, first of all, this part here, it's going to integrate to ln mod 2p minus 1. But, of course, we have to divide by the derivative of the inner part here, so over 2. You could do a full integration by substitution to show this. It's such a basic integral that really you need to be able to do this kind of integral very quickly. So the next part is simply ln mod p, and this equals a half sine t plus c. Let's substitute in this piece of information up over here. P equals 1 when t equals 0. So this gives me ln of 1 minus ln of 1 equals 0 plus c. So c, very conveniently, equals 0. This then gives me ln of mod 2p minus 1 minus ln of mod p equals a half sine t. So on the left-hand side, I can write this as ln of 2p minus 1 over p, and I think we have the information that p can't be negative, so we can remove the modulus sign, so that equals a half sine t, and we've done the part that we needed to. Now, this equation can be rearranged to give this result over here. Find the greatest and least values of p predicted by this model. Now, it looks like something's missing here from the question. It should be t subtract e to the half sine t there. So we want to try and find the maximum and minimum values of p predicted by this model. So let's think about the values of sine t. So sine t can be between 1 and negative 1. So if sine t equals 1, that means that p would equal 1 over 2 minus e to the power of a half. If sine t equals negative 1, this means that p would equal 1 over 2 minus e to the negative a half. Now you can use a calculator to evaluate these. This one is equal to 2.847 and this one is equal to 0.718 approximately. So we can see from here that this one is the maximum value and this one is the minimum value predicted by the model. So example 4, we have a hemispherical bowl of radius 10 centimetres filled with water to a depth of x centimetres. It can be shown that the volume of water is given by this result here. Water is poured into a leaking hemispherical bowl. Initially, the bowl is empty, so we know when t equals 0, v equals 0. After t seconds, the volume of water is changing at a rate given by this equation here, where k is a constant. So we need to find dv by dx and show that this result is true. So there's quite a lot to do in this question. So, part 1. To find dv by dx, we can simply differentiate the result that's up here. So that's pi, brackets, 20x minus x squared. Very simple derivative. Now, hence show this result here. So have a look at all of the different derivatives that seem to be involved in this question. We have dv by dt, dx by dt, and dv by dx. So this really means that we need to be thinking about the chain rule. So we know that dx by dt would be equal to dv by dt multiplied by dx by dv. Think about that carefully. So dx by dt is dv by dt multiplied by dx by dv. It's not quite what happens, but imagine the dv by dv parts cancelling. So what do we know? Well, dv by dt, we've been told, so that's k, brackets 20 minus x, and dx by dv will be the reciprocal of dv by dx. So it will be 1 over pi 20x minus x squared. Let's factorise this part here. And then hopefully we can see the cancellation that we are left with. So we now know that dx by dt is equal to k over pi x, and we can then simplify multiplying both sides by pi x, so we get pi x dx by dt equals k, and we've done what we needed to. Now, part 2, solve this differential equation and hence show that the bowl fills completely after t seconds, where t is given by this value over here. So part 2, we need to separate the variables in this differential equation. So x on the left-hand side, so we have pi, the integral of x dx equals k, the integral dt. So the left-hand side becomes pi x squared over 2, the right-hand side becomes kt plus a constant. Now, what do we know? Well, we know initially the bowl is empty, so that means that not only does v equal 0 when t equals 0, well, x must equal 0. There can be no depth of water if there's no volume of water. So that tells us straight away, if x equals 0 when t equals 0, then c has got to equal 0 as well. So this then gives us the result that pi x squared over 2 equals kt. Now, what happens when t equals 50 pi over k, which was the information that we were given over here? Well, let's substitute that in. So t equals 50 pi over k. Let's input that information for the time. So that gives me pi x squared over 2 equals k multiplied by 50 pi over k. And we immediately find some simplification happens. And this gives me x squared equals 100, so x equals 10, which means that the radius of the bowl equals, the radius of the water is the same as the radius of the bowl, 10 centimetres, so i.e. the bowl is full, completely full. So once the bowl is full, the supply of water to the bowl is switched off and water then leaks out at this rate here. Now, look at the units on this, centimetres cubed per second. Sometimes that can help you work out what information you've been given. It's volume per second, so it's dV by dt, and it must equal negative kx because the water is leaking out. So, part 3, we have to do something similar to last time. Remember, dx by dt is equal to dx by dv multiplied by dv by dt. Now, dx by dv we had from the previous question, and it's 1 over pi 20x minus x squared. And dv by dt is this time negative kx. Now, let's simplify this. So 1 over pi x 20 minus x multiplied by negative kx. And this is dx by dt. So I can cancel a value of x here and here. So we'll then multiply it by the denominator. So we get pi 20 minus x dx by dt and negative k on the right-hand side. So we've done the first part of the question. Now, part 4 requires us to solve this differential equation. So solving the equation, make some space over here to do this. We need to take this and we want to separate the variables, so we have x on the left-hand side, so pi 20 minus x dx integral of, and on the right-hand side we'll have negative k integral dt. The k could be inside the integral sign as well. So very, very simple integration to do. So we have pi 20x minus x squared over 2 equals negative kt plus c. Now, remember we're starting this from when the bowl was in fact full, so we're restarting the time at t equals 0 from the point when the bowl is full. At this point, x is equal to 10 because the bowl of water is full, so the radius of the water is the radius of the bowl, which is 10. So substituting in this information gives us pi 200 in the brackets here minus 100 over 2 equals 0 plus c. So this gives me c equals a value of 150 pi. So pi 20x minus x squared over 2 equals negative kt plus 150 pi. So there's my solution to my differential equation. Now, hence show that the bowl empties in 3t seconds. Well, the bowl is empty. That means that x equals 0. So if x equals 0, well, the whole of the left-hand side becomes 0. So we end up with 0 equals negative kt plus 150 pi. Let's rearrange this. It tells us that kt equals 150 pi and t is equal to 150 pi over k, which is equal to 3 multiplied by 50 pi over k, and if you remember from the earlier part of the question, that is t. So the bowl empties and has an x value of 0, radius of water of 0, when the time is 3t. So example 5. We are told that scientists can estimate the time elapsed since an animal died by measuring its body temperature. So question has variables of time and temperature. Assuming the temperature goes down at a constant rate of 1.5 degrees Fahrenheit per hour, estimate how long it will take for the temperature to drop from 98 degrees to 89 degrees and 98 degrees to 80 degrees. Okay, so we're told in the question that the temperature goes down at a constant rate of 1.5 degrees Fahrenheit per hour. So from 98 degrees to 89 degrees Fahrenheit, that is a jump of 9 degrees. So 9 divided by 1.5 gives us a value of 6 hours. And 98 to 80 is 18 degrees difference. So 18 divided by 1.5 gives us 12 hours. So in practice, rate of temperature loss is not likely to be constant. A better model is provided by Newton's law of cooling, which states that the temperature, theta in degrees, is given by this differential equation here, where theta 0 is the air temperature and k is a constant. Show by integration that the solution of this equation is this, where a is a constant. So the fact that it says show by integration means we've got to separate the variables and integrate. We cannot just verify that this works by differentiating. So we're going to separate the variables first of all for part 2. So I can say that 1 over theta minus theta 0, remember that's a constant theta 0, integral of, with respect to theta, equals negative k integral dt. Left hand side will give me an ln result, so ln of mod theta minus theta 0 equals negative kt plus c. And then I'm going to take e to the power of both sides, so theta minus theta 0 equals e to the negative kt plus c. We've been here before. Let's split up the right hand side like that, and then we can simply say that theta equals theta 0 plus a e to the negative kt, where we have allowed e to the c to equal a different constant a. Well, the same constant given a different letter a. So the value of theta 0 is 50 and the initial value of theta is 98. So that tells us when t equals 0, theta equals 98 degrees Fahrenheit. And the initial rate of temperature loss is 1.5 degrees Fahrenheit per hour. So that tells us when t equals 0, d theta by dt is negative 1.5. So find a and show that k is equal to this value. So let's remind ourselves of the equation that we have, which tells us that theta equals theta 0, which we now know the value of, plus a e to the negative kt. Let's substitute in, first of all, this information and see what we can work out. So that tells us that 98 equals 50 plus a, because e to the power of 0 is, of course, 1. So this gives us that a is equal to 48 as a starting value, And we can now then say that our equation is theta equals theta 0 plus 48e to the negative kt. Now differentiating that, d theta by dt gives us negative 48k e to the negative kt. And we're now going to substitute in this information up here when t equals 0. So that tells us that the rate is negative 1.5, which equals negative 48k, and of course e to the negative kt will still be 0 because t is 0. So k is equal to 1.5 divided by 48, which is 0.03125, which is what we were required to find. So part 4, use this model to calculate how long it will take for the temperature to drop from 98 degrees Fahrenheit to 89 degrees Fahrenheit. So we know that when T equals 0, that's when the temperature is equal to 98 degrees Fahrenheit. So let's make the temperature equal to 89 degrees Fahrenheit. So that means I have 89 equals 50 plus 48 e to the negative kt. But of course we know the value of k. I'm substituting into the equation up over here, but with the known values. So let's rearrange this. So what do we have? We have 39 equals 48 e to the negative kt. 39 over 48 equals e to the negative kt. And taking a natural log of both sides will allow me to calculate negative kt. And I can simply divide by the negative value of k to give me t. So that gives me t equals 6.6444 ... So let's say 6.6 hours to 3 significant figures. Now that's the answer to part A. The answer to part B, we do something very similar. So theta equals 80 degrees this time. So 80 equals 50 plus 48 e to the negative kt. And it shouldn't take long to get you to the fact that negative kt is equal to ln of 30 over 48. And you will find that the time is equal to 15.040011. So that's 15.0 hours to 3 significant figures. Now, part 5 asks us to comment on the results obtained in part 1 and part 4. Now, in part 1, the answer to this part of the question here was 6 hours in part 1, and the answer to this part of the question was 12 hours. So we can see that the models disagree at the first example, but they disagree a lot more in the second example. Now, why is that? Well, the initial temperature loss is 1.5 degrees Fahrenheit per hour, and the first model assumed that this was constant, but the second model assumed that this was then part of a more complex model. So obviously, for a greater temperature decrease, the models will disagree more, because earlier on, the rate of decrease of temperature won't be that different to negative 1.5, which is why in the first example, the two models are not that different. So what we can say for part 5, for the comment, the models disagree more when the temperature loss or the temperature decrease is larger. So there's a greater discrepancy between the answers produced by the models in this sort of situation when you're looking at a larger temperature drop. If you're looking at a smaller temperature drop like here, the models actually don't disagree that significantly. Right, example 6, the last example. So some years ago, an island was populated by red squirrels and there were no grey squirrels. Then grey squirrels were introduced. Now the population, X in thousands, of red squirrels is modelled by this equation here. T is the time in years, A and K are constants, and here are some initial conditions. When time is 0, X is equal to 2.5. So first part, a bit of differentiation. Part 1. We need to show that the derivative is this. So dx by dt, I'm going to rewrite this as a bracket 1 plus kt to the negative 1, although you could use the quotient rule if you wanted to. I'm going to use the chain rule. So negative a, 1 plus kt to the power of negative 2. Don't forget to multiply by the derivative of the inner function here, which is simply k, which then gives us dx by dt equals negative ak over 1 plus kt all squared, which we can simplify as negative k over a multiplied by a over 1 plus kt all squared. And you can see very clearly the a squared will cancel with the a in the denominator to leave you with a single a in the numerator. And this, of course, is negative k over a x squared, as required. Now, part 2, given that the initial population of 2.5 thousand red squirrels reduces to 1.6 thousand after 1 year. Calculate A and K. So we have this information here. Let's sub in the first piece of information. So that tells us that when t equals 0, x equals 2.5. So that tells me if I substitute into this result here, 2.5 is equal to A over 1. T is 0, so kt is 0, so a equals 2.5. And if I then substitute in the second piece of information, that tells me that 1.6 is equal to a, which I now know is 2.5, over 1 plus k, and it's a very simple matter to rearrange this and find k. So k is equal to 0.5625. Now, part 3, what is the long-term population of red squirrels predicted by this model? So look at the fact that x is equal to 2.5 over 1 plus 0.5625t, and long-term population, we know that means t approaches infinity. So that means if we think about this equation x, if t is going to become very, very, very large, this t here, this 1 here, doesn't become particularly important to this. And what we have is 2.5 over a very large number, because even though you're multiplying t by 0.5625, imagine if t was equal to 10 million. You'd end up with a very large denominator. So in fact, this 2.5 doesn't become very important either, and x ends up being approximately 0. So as t approaches infinity, x approaches 0, so the long-term population is 0. So the population y, in thousands of grey squirrels this time, is modelled by this differential equation, and here are our initial conditions as well. So part 4, a bit of partial fractions work. So let's start there. Part 4. Express 1 over 2y minus y squared in partial fractions. So let's remember that that is 1 over y bracket 2 minus y, like so, first of all. And we'll write that as a over y plus b over 2 minus y. So we get a bracket 2 minus y plus by. Let's allow y to equal 0, which gives us 1 equals 2a. So we instantly know a is a half. Let's allow y to equal 2, which gives us 1 equals 2b. So b also equals a half. So our partial fractions are 1 over 2y plus 1 over 2 bracket 2 minus y in our answer to part 4. Hence show by integration that we get this result. So what we're going to do is we're going to separate variables in our differential equation and integrate. So the left-hand side will become the integral of 1 over 2y minus y squared dy. The right-hand side will become the integral of dt. Now the left-hand side, we know that we have expressed this single fraction as its decomposed partial fractions, like so. So on the left-hand side, we know we're integrating 1 over 2y plus 1 over 2 minus y dy. I could factorise the half out of the whole integral. I could do this as two separate integrals. It doesn't really make a difference. The right-hand side integrates to t plus c. Now, let's integrate the left-hand side. So I get a half ln mod y, and then minus a half ln mod 2 take away y equals t plus c. I want to substitute in these initial conditions here before we do anything further. So when t equals 0, y equals 1. So we'll get a half ln 1 minus a half ln 1 equals 0 plus c. So c is equal to 0. So this then tells me that I get a half ln of mod y over 2 minus y equals t. So going from this stage to this stage here. Now we can multiply across by 2. So that gives me ln of y over 2 minus y equals 2t. I think there's a subtraction missing there in the question. And I think we can ignore the modulus sign here because the y value is never going to result in a negative in this question. Right. Part 5, show that y equals this result over here. So let's make a little bit of space here. We just need to do some rearranging of this result. So e to the power of both sides leaves us with y over 2 minus y equals e to the 2t. Multiply both sides by 2 minus y, which gives us this. Expand. Y equals 2e to the 2t minus ye to the 2t. Collect the y terms on the left-hand side. Y plus ye to the 2t equals 2e to the 2t. Factorise y bracket 1 plus e to the 2t equals 2e to the 2t. And then divide by the bracket, so y equals 2e to the 2t over 1 plus e to the 2t. Now we've seen this idea before. They just want us to do a slight revision to get to this format here. So we want the numerator to just be 2. Let's multiply the numerator and the denominator by e to the negative 2t, which means in the numerator we get 2, and in the denominator we will end up with e to the negative 2t plus 1 as required. Now, last part of this, what is the long-term population? So allow t to approach infinity. Now, if t approaches infinity, then e to the negative 2t will approach 0, will become very small, which means that y will be approximately 2. Because, of course, you're allowing this part here to approach 0, so you're left with 2 over 1, which gives you y value of 2 for the long-term population. But let's remember that this population is measured in thousands, so actually the long-term population is 2,000 grey squirrels.